Hi, welcome to Coursera's Instrumental Analysis class. I'm Professor Colvin, and this is Lecture 6. We're moving through a couple of mini lectures that cover error in analysis. So in this lecture, we're going to be talking about explaining and defining error bars in terms of a confidence limit. So in the last module, we learned that if you just take the standard deviation of a set of replicate measurements, then you can use the standard deviation as your error bar or your plus minus description of random error. But there's something really limiting about that, and that is you can't really control how tight your error bar is. It might be that you want to give a really big error bar to be really sure that you capture all of the future measurements that might occur. Or maybe we want to give a narrower error bar. So when you describe and provide an error bar, you need to tell the audience, this is plus or minus, and in future measurements, I am X% confident that they will fall in the range I've given you. And so that's basically defining error bars with a confidence limit. So today I'm going to talk to you about sort of practically how to do that and show you a couple of examples. So this is part of our discussion of how to convey uncertainty. And what's really important about today is we're really going beyond, I think, sort of the freshman chemistry level and really talking about if you want to be more precise into talking about your imprecision, you're going to use confidence limits, which means you're going to modify the error bar, you're going to modify the standard deviation in a very prescribed way. And you're going to tell the audience not just what the error bar is, but what the confidence limit was that you used to calculate that error bar. And that's a really important and valuable set of data for predicting how future measurements might match up to the one that you took. Or, flipping another way, how confident you are that the true value lies between the range that you gave. So how certain is your uncertainty? So going back to this picture, which we had from the last one, this is basically the bell curve. And we talked about how if you provide a standard deviation to your readers, when you also provide a measurement of replicates, so you give an average plus or minus the standard deviation, you're in effect telling them that 68.3% of future measurements would fall within those bounds. And converse way, you're 68.3% confident that the average you provide is indeed the true average if it's within those plus minus bounds. But what if you want to be more confident? You want to say be 90% confident. We need a way of modifying the standard deviation that helps you do that. And that's where confidence limits come into play. So basically what we're going to do in a confidence limit is we're going to start with a standard deviation. So we're going to assume that you did a series of replicate measurements. That's kind of the 0th order thing you have to do to characterize random error. But what we're going to do is we're going to multiply that by a factor. And that factor is going to reflect something about our confidence limit. So before I talk to you about where the factor comes from, let's just sort of reason through how to think about it. So if in this example, I simply gave you the answer and this was 1, well, then you're going to be 68% confident that the new measurements are in this range. And that's just the 0th order case we had before. Now, if we have a factor less than 1, so let's say it's an average plus or minus 0.5 times our standard deviation, then we're going to have less confidence that future measurements would be in that range. And if we did x bar plus or minus, I don't know, 4s, well, that's a really big tent. Odds are a lot of measurements will be more confident that the true value lies in the range we provide. So pictorially then, if you do the middle one, you're saying that of all measurements shown in blue, the red here is bounded by the errors. If you go to a small factor, so you multiply by a number less than 1, then you're going to be less confident, and future measurements will be less of a total fraction of all the measurements. And likewise, if you expand the error bars, you're going to have a higher degree of confidence that the true value is within the boundaries that you provided. So how do we get that factor? Well, that factor comes from something called a t-table. A t-table is a calculated set of t-values that come from the mathematical truths that surround Gaussian distributions. So I'm not going to derive it for you except to say you can find it a lot of places on the web. And what a t-table has is it's going to have at the top a confidence limit, and on the left-hand side, the rows are going to be the degrees of freedom. So let me talk through what that means. So on the left-hand side of a t-table are going to be a series of rows. And we're going to start with, let's say you just made one measurement. Well, if your standard deviation comes from 1 or 2 or 3 measurements, well, it's not a very precise standard deviation. And so in fact, you're going to have more uncertainty associated with that uncertainty. So the factors you're going to use in front of it are going to be larger. Likewise, if you took a lot of measurements, the degrees of freedom will be large and the factor will shrink. So one part of a t-table isn't just about the confidence, it's about how many measurements you took. Because if you're reporting at an error bar and you've only done 2 measurements, well, that's a lot different than reporting on an error bar with 25 measurements. But if you just report the standard deviation, there's no way to tell your reader how many measurements you took. So one thing that t-table and confidence limits do is they take in and fold in how many replicate measurements did you actually collect. Now the columns in a t-table represent how confident you want to be. So on the left-hand side are numbers you're going to use if it's okay to be less confident that your value is within the boundaries you provide, but if you want to be super confident, then you go over to the right. And as you're going to see, the factors that you put in front of the standard deviation change. So there's 2 things that this t-table is going to do for you then. It's A, going to let you specify how confident you want to be that the error bars you gave really do encompass the true value, assuming there's no systematic error, of course. And it's also going to deal with the other problem, which is that if you just report a standard deviation out on an average, you haven't told the reader anything about how many measurements you made. And so folded in to your error bar and the confidence limit that you're using is how many measurements you took. So here's an example of a t-table. You can find a lot of these on the web. And as you can see, as you go down in degrees of freedom, these are basically n minus 1. So it's a number of measurements minus 1. And look what happens to your factors. They get much, much, much smaller. So as you get down to over 20, they don't change much at all. And what you basically are saying is by the time you've made 20 measurements, you've made a pretty good estimate of what the error bar should be, meaning you've sampled enough replicates to really get a good measure of your random error. Then the other thing you'll notice is, and as you can see there, as you go and you want more confidence, boy, those error bars, look at this. If you only do 1 measurement, you want to be 99 point, or actually 2 measurements, and you want to be 99. If you only did 2 measurements and you want to be 99.9% confident, you're going to have to multiply your standard deviation by almost 600. That's a really big tent because you just don't have that much information. And you want to be really confident that future measurements are going to lay within your boundaries or that your true value is encompassed by those. But look what happens if you're willing to live with only 90% confidence. You only have to multiply and make your error bars increase by 6.31 over the standard deviation. So this formula here is an important one then, because it says what you have to do. You're going to modify your standard deviation by the t-value and n. And the only thing I'm going to point out that can be confusing for students is that on the bottom you're going to have the number of measurements, but when you look up in the t-table chart, remember you're looking up n minus 1. So degrees of freedom are not the same as the number of measurements. So there are 2 different ways that you might find yourself using confidence limits. In one way, you might have an experimental set of data and you can find the standard deviation from that. And you wish to report the error bars and tell your readers what the confidence limits are on those error bars. Kind of a more higher level description of error. In the other case, you might be given the standard deviation of a method, which is effectively its real sigma. And that's assuming that you've done hundreds and thousands of measurements. And so you're applying that method and you want to know, gee, okay, I don't need my error to be as good as that. I don't have time to do 1,000 measurements. But what if I did 10? How good will I be then? So another way of using confidence limits is actually to flip and to calculate how many measurements you have to make in order to achieve a certain level of precision. Okay, so in this first example, you've got a whole bunch of measurements of zinc in capsules, and you want to find the error bars on the average value of zinc in the tables and use the t-tables to get a 95% confidence limit on that error bar. So the first thing you're going to do is calculate the average and the standard deviation. Remember, the standard deviation, or S, is an important part of that formula. So to get this, you're going to just say average plus or minus t, where t is the number. We're going to look this up. So you're going to look that up in the t-table. And you're just going to say, there's my average. And to get my error bars, I have to look up t and I have to divide by the square root of n. So we calculated the standard deviation to be 0.47. We went to the t-table and we used a degree of freedom of 6 and a 95% confidence limit, and we found a t of 2.45. And notice, whereas we used a degree of freedom of 6 on the table, we used an n of 7 in this calculation. So we have t, s, and n, and we just apply this formula to calculate what the error bar would be. And when we do that, we find that we get 0.4 milligrams of zinc, and you would say 95%. There's a couple of different ways of conveying confidence limits that I've seen. Often a vertical bar with a 95% at the bottom is common. Sometimes you might see a slightly different approach. A parentheses that gives you the confidence limit and the number of measurements that you collected. So you'll see it reported out either way, but when you see that percentage, you know that somebody modified the standard deviation according to a t-table to give you a more precise characterization of what your error is. Let's do the reverse now. Let's do the case where you have a methodology and you want to know how many measurements do I have to make in order to get a precision that's satisfactory for me. This is a really common kind of, well, the first thing you're going to do is, like always, you're going to write down the formula, which is x bar plus or minus ts over square root of n. Except in this case, what we're interested in is just the error. We took this as our error, and we set it equal to 0.42 because that's what the problem asked us. That's the error we wish to achieve. And we also know that we want 95% confidence limits on this. So if error is equal to 0.42, then we're going to have to set that error equal to t sigma over root n. So we need t, which we're going to get from the t-table, sigma, which is actually given here, and square root of n, which we don't know the answer. So n is what we're actually solving for. So when we do this then, n just goes up. Now, an important thing about how we got t. When a method gives a standard error, what that means is that the degrees of freedom is equal to infinity. In effect, NIST is telling you we did thousands of measurements, and after thousands of measurements, here's what we found. So when you're given a standard error in a method, and you're trying to calculate, okay, I'm going to use this method, what's going to happen for me, you assume that that method was taken with an infinite number of degrees of freedom. In any case, when we do this, we'll see that we only have to take 2 measurements to get an error under 0.42. So I hope I've given you some idea of what confidence limits are. There's a handout online, which is something that I wrote up to describe this, I hope in more detail for you, because I anticipate it may be new material for many of the chemists listening to these lectures. And we're also going to be practicing it a lot on our problem set. Remember that the point of using a confidence limit is it addresses 2 of the limitations of a standard deviation when you report out an error bar. First, it tells you something about the size of your data set. It gets incorporated into the error bars. It also lets you specify for the reader how confident you are that your true value lies within the boundaries that you gave. And so it's ultimately a better way of expressing error, although in point of fact, you won't see it used all the time. You'll see it used in some circumstances. And you should strive for when you can to try to report your error bars using a confidence limit kind of approach, so your reader has a lot more information than just the standard deviation of your replicate measurements. Thanks so much. See you next time.